Hi everyone, this is video number 4B. In this video, you are going to model a phase change on a heating curve or a cooling curve. You're going to calculate the heat that must be absorbed or released to change the temperature of a substance or change its phase. You're also going to learn about how to round your answers to the correct number of significant figures. So with that said, let's get started. Here are some questions. Please read the following statements and see if you can answer them. Tell me whether they're true or false. And maybe you can perform some calculations here as well. All right, if you need more time, just pause the video and try to answer them. Let's continue. Okay. Heating curves and cooling curves. Let's read together. Okay, so phase changes, we discussed that earlier. Solids to liquids to gas, these are all, or backwards, gas to liquid to solid, these are all phase changes. We also have solid to gas, sublimation, gas back to solid, deposition. Heat that is needed to break apart the bond. Heat is needed to break apart the bonds and keep the, and I guess separate the atoms. Okay, so here's what a heating curve would look like. We have two horizontal lines, usually. If let's say I'm going from a solid to a liquid to a gas, I would have one horizontal line for going from a solid to a liquid, and I would have another horizontal line for going from a liquid to a gas. So here's the first horizontal line for going from a solid to a liquid, and here's the second horizontal line for going from a liquid to a gas. So here, the temperature, notice, from the second point A, you began melting, to the point where you stopped melting, the temperature did not change, and that is because all the heat that you're adding is actually being used to break apart the bonds. Same thing here when it comes to evaporation. At point C, that's when you started evaporating. At point D, that's when you stopped evaporating. And notice the temperature also did not change. We're still at this temperature because all the heat that you're using, that you're adding, is actually being used to break apart the bonds, to change them from a liquid phase to a gaseous phase. All right. We also notice here that the amount of energy that's needed to evaporate something is so much higher, because look at this line from C to D. It takes so much time to evaporate something than it does to melt something. Notice the melting here is very little. The distance, the point from A, the line from point A to B is much shorter than the line from point C to D. Okay, from C to D we have what we call a heat of vaporization. From A to B we have what we call heat of fusion. So the heat of vaporization is the heat that you need to add to vaporize something, to vaporize 1 gram of the substance that you're using. The heat of fusion is the heat that you need to add to melt 1 gram of a substance. So here, if we look at the reference table, we see on table, I believe table B, taking a look right here, we have the heat of fusion for water. We need 334 joules. Joules is the unit that we use to represent the amount of heat that we gain or lose. So 334 joules are needed to melt 1 gram fusion, melt 1 gram of water. So if you need 334 joules to melt 1 gram of water, obviously you would need to release 334 joules to freeze 1 gram of water. So HF is going to be used for melting. You add HF if you're melting, and for freezing, you remove HF. It will be negative HF if you're freezing. Vaporization is the same way. You need 2,260 joules of heat to turn 1 gram of liquid water to a gas. And obviously, you'll have to remove 2,260 joules of heat to turn 1 gram of gaseous water back to a liquid. Here we have a specific heat capacity, and that is the amount of heat that's necessary to raise the temperature. So we talked about the heating curve. Okay, so let me draw a better heating curve right here. So here's where your phase changes take place. That's where your HF and HV take place. And here, from here, this line here is where you're actually raising the temperature prior to melting the substance. Here is where you're raising the temperature. Here's where you're raising the temperature. So there's a formula on table T that says Q equals MC delta T. So to calculate the amount of heat that's necessary to raise or drop the temperature, you use this formula. And that is the mass multiplied by the specific heat capacity, which is right here. For water, it's 4.18 joules per gram times Kelvin. Okay? And delta T is going to be the change in temperature. So let's say I want to raise my temperature. Let's say I want to raise the temperature of a 15 grams of water from 5 degrees to 7 degrees. All you have to do is do 15 multiplied by the specific heat capacity, MC delta T. The mass is 15. The specific heat capacity, C, is 4.18. And the change in temperature, in this case, from 5 to 7, is going to be 2 degrees. So that's your delta T. So you multiply 15 by 4.18 by 2, and you will get your final heat that's necessary to raise the temperature of water by 2 degrees. To raise the temperature of 15 grams of water by 2 degrees. Okay, so this is pretty much how to calculate the heat necessary to raise the temperature of water or drop the temperature of water, or to melt water or to evaporate water, or to evaporate or melt or raise the temperature of any other substance. Okay, let's go back. We talked about the phase changes taking place at the horizontal lines. Additionally, we talked about how the temperature does not change. So temperature is really just kinetic energy. That's what temperature is all about. It's simply just kinetic energy. So temperature is a measure of the average kinetic energy. So how fast the particles are moving. We use temperature to measure how fast the particles are moving. Again, the temperature does not change during phase changes, which means that the kinetic energy is constant at the horizontal line. So kinetic energy is constant. But what happens is the potential energy actually increases at the horizontal lines. On the other hand, at the slanted lines here, where we raise the temperature, obviously we're raising the temperature, so the kinetic energy, notice how the K is actually showing you slanted lines already as it is. So you'll always remember that the kinetic energy changes at the slanted lines. Kinetic energy is increasing or decreasing at the slanted lines. It will increase in a heating curve and it would decrease in a cooling curve, while potential energy remains constant on the slanted lines. Remains constant. Okay. Here are some questions that may come up. Let's say here, you may be asked, how much time does it take to condense the substance presented in this cooling curve? So this is a gaseous phase. The highest temperature is gas from B to A. That's all your gas. This is your liquid, and this is your solid. So here you will condense. From B to C. Here you will freeze from D to E. So how much time does it take to condense? Well, we begin condensing at the 3rd minute. I'm assuming this is in minutes. And we stop condensing at the 6th minute. So it takes about 3 minutes. From 3 to 6, it takes 3 minutes to condense this substance, while it starts freezing at 8 and stops freezing at 10. It takes 2 minutes to freeze this substance. So freezing from D to E, condensing from B to C. Okay? Heating curve obviously requires heat, and if something requires heat, we call it an we say that that's endothermic. Endothermic phase changes. These are phase changes that require some sort of energy, heat, light, or electrical energy. For example, melting, boiling, sublimation. These are all endothermic because they require heat. Think of endothermic as enter heat. So if I was to actually represent this in an equation or a reaction, I would say H2O solid for ice plus heat will yield H2O liquid. So solid ice plus heat will give me liquid water. Okay, notice how I'm entering heat. So think of this arrow as a door which you enter from the left and you exit from the right. Enter, exit. On the other hand, exothermic phase changes release energy, for example, freezing, condensation, and deposition. So let's say, for example, here, H2O, liquid. If I want to turn it into H2O solid, I would have to exit the energy. In this case, I would have to have energy on this side, on the right side. That's where my products are, and this is where my reactants are. So exo, exit, endo, enter. Okay? Reactant side on the left side of the arrow, product side on the right side of the arrow. The product is what you're producing, the reactants is what you're combining or mixing together, the things that you need to create your products, your desired products. Okay? A phase equilibrium occurs in sealed containers when the rate of evaporation equals the rate of condensation. So let's say you have a flask here and it has it's sealed from the top, and you have some sort of heat here, and you have some liquid water here. You'll eventually create a phase equilibrium in which the liquid water will turn into gas, and the liquid water will condense back again and turn back into liquid, and then it will turn into gas, and then it will turn into liquid. So a phase equilibrium is when the rate of the rate of evaporation equals the rate of condensation in this case, or when the rate of freezing equals the rate of melting. This will only happen when you have a sealed container. We talked about the vertical lines. In the previous video, we talked about how systems in nature will favor lower enthalpy. They like to release heat, they lose energy, and higher entropy they usually get messy. And we mentioned the plants as an example. Eventually plants lose all their energy and eventually they die, just like all other systems in nature, all other living organisms. And also, if left untaken care of, plants get really bushy and they get really messy, just like everything else in nature as well. Talked about how entropy is the random arrangement of particles. Another thing you should know is that we'll talk more about this when we get to thermochemistry, but energy will always flow from hotter substances to colder substances. So let's say you have a hot container here that contains a lot of hot food. And you put that next to a cup of water, or maybe a can of Pepsi. Eventually your can of Pepsi will get a little warmer, and because the heat flows from the hot food into your Pepsi. We talked about this. Let me just go back and remind you of this. So the slanted lines will always represent the phases of matter, while the horizontal lines represent the phase changes. So here are the phases of matter. Lower temperature will always be the solid. All the way at the bottom will always be the solid. So in the heating curve, this would be your solid. In the cooling curve, this will be your solid. This would be your liquid. This would be your gas. This would be your liquid. This would be your gas. This is your phase change, A to B. This is your phase change, C to D. This is your melting, A to B. This is your evaporation, C to D. Here again, we're going back. Gas to liquid, this is your condensation, B to C. This is your freezing, D to E. Okay? Another thing you should also remember, that when you're drawing a heating curve or a cooling curve, see what the question is actually asking you. If you're drawing a heating curve to represent the melting of a substance, let's say a heating curve that represents the melting of water, I don't need to draw this because I'm only melting water. So this is evaporation, that's irrelevant. This is gas, that's irrelevant. Melting water is just going from a solid to a liquid. So this would be your melting. That's it. That's all you need to draw. You don't need to draw the whole thing. Okay, you only need to draw solid line, melting line, and the liquid line. That's it. That's melting. If I was to draw sublimation, for example, sublimation is changing from a solid to a gas directly. You also don't need to draw the entire curve. You can just simply just draw solid line, sublimation line, and then the gas line. That would be your heating curve to represent sublimation. Deposition the opposite way. Gas back to solid and deposition. Okay, that's pretty much it. Talked about this. Point B represents constant condensation point, which equals the melting point, which is point B. Let's go back here. Point B represents the condensation point, which equals the evaporation point. So condensation is at point B, evaporation is at point C. This is where you begin to condense. This is where you begin to evaporate, going backwards. Evaporation happens in this way, in that direction. Condensation happens in this direction. So this should say point B represents condensation, which equals evaporation. The condensation point equals the evaporation point. Point means temperature, so condensation temperature equals the evaporation temperature. So if I'm looking at this here, the evaporation temperature would be, the evaporation point would be point C, the melting point would be point A. This is where you begin. It's very important that you know that the condensation or evaporation or melting, it's when you begin to condense, you begin to evaporate, begin to melt. We talked about that already. We talked about this. This is pretty much the same stuff we already discussed. You can read this. We could talk about this a little bit. Heat is measured in unit joule or calorie. Refer to Table C for unit conversions, factors, or Table D for unit abbreviations. Two standard international units are liters, meters, and grams. Table C examples: 5 milliliters equals 5 times 10 to the negative 3, 5 kilometers. So let's take a look at Table C. If you have to do any conversions, you can refer to Table C. So for Table C, we have the conversion units. So as mentioned here, the standard international units are liters, meters, and grams. Going back, you got liters, meters, and grams. Okay, so if you are converting a gram to a milliliter, you simply just take your grams, multiply them by 10 to the negative, the factor 10 to the negative 3, and you get your milligrams. If you're converting grams to nanometers, or nanograms, grams to nanograms, you take your grams, you say you have 5 grams, multiply that by 10 to the negative 9 in your calculator, and you will get nanograms. Okay? Let's say you're going from nanograms to milligrams. From nanograms to milligrams, notice the difference. Let's say you have 5 nanograms and you're going to milligrams. So you're going from negative 9 to negative 3. The difference between negative 9 and negative 3 is negative 6. Okay, so you're going from 5 nanograms to milligrams. So obviously milligrams are bigger, so milligrams are much larger than nanograms. So a whole lot of nanograms would be equal to very little milligrams. A whole lot of nanograms, a lot of nanograms would equal to very few milligrams. So since the difference is 10 to the negative 6, like we said earlier, so your 5 nanograms multiplied by 10 to the negative 6 will give you your answer in milligrams. Okay? That is simply how you convert. And if you're going backwards, obviously, you'll be multiplying by a positive. So if you had 5 milligrams and you wanted to convert that to nanograms, so very few milligrams equal a whole lot of nanograms. Very few milligrams equal a whole lot of nanograms. So I will be multiplying 5 by 10 to the 6 in order to get how many nanograms I have, equivalent to 5 milligrams. So 5 times 10, so 5 milligrams would probably be 5 million nanograms. Okay? Always ask yourself this logical question. Am I converting to a smaller unit or am I converting to a larger unit? All right? Going back to here. Significant figures. For the Regents, you only have to know how to round your answers to the correct significant figures if you're actually multiplying numbers. So the PA rule, simply, you can read this later if you'd like, but I'm gonna explain it here for the sake of time. So PA rule. P stands for a present decimal, and A stands for an absent decimal. So absent, a number that has an absent decimal does not have a decimal, or a number that has a present decimal, so does have a decimal. So let's take, for example, 2.05. So this number obviously does have a decimal. So according to the PA rule, I will approach this number from the left side. Okay, that's your first step. Approach the number from the left. Underline the first non-zero number, in this case coming from the left. This is the first non-zero number I see. And underline all the numbers that follow that first non-zero number. So I'm going to underline this one as well, and I'm going to underline this one as well. So the total number of numbers that I underlined are 3. So therefore this has 3 significant figures. It's that simple. Let's assume now you don't have a number that has significant that has a decimal. Let's say, for example, 10050. In this case, there's no decimal here, so the decimal is absent. According to the PA rule, I will approach this number from the right side. I will do the same exact thing. Underline the first non-zero number that you see. So I'm not going to underline this 0, I'm going to underline this 5. I underline the first non-zero number, and I underline all the other numbers that follow. So in this case, this number has 4 significant figures. Okay? Now, if I'm multiplying these two numbers together by each other, if I'm multiplying by each other, or I'm dividing them by each other, all I have to do is simply round my final answer to 3 significant figures. Why? Because that's the rule. You always round your answers to the least number of significant figures possible. So you'll first figure out how many significant figures your first number has, then you figure out how many significant figures your second number has, third number, fourth number, fifth number, sixth number, and then at the end, you see which one has the least number of significant figures. After you perform all your calculations, your multiplications, your divisions, you will round your final answer to the least number of significant figures. So let's say, for example, I am multiplying 5 by 2.0. So 5 multiplied by 2.0, 5 only has 1 significant figure. 2.0 has 2 significant figures. So my final answer is going to have 1 significant figure. So 5. So sorry about that. So 5 times 2.0 is going to equal 10. Now you ask yourself, is 10 1 significant figure? The answer is, approach it from the right. Decimal is absent. Coming to the corner. Approach it from the right. The decimal is absent. So look for the first non-zero number. It's 1. There's only 1 number that's underlined. Therefore, 10 is actually 1 significant figure. I don't have to round it. I don't have to change it. However, if you had 10.0, that would actually be considered wrong, because that would be 3 significant figures. Okay, so that's pretty much it for significant figures. Now I'm going to go back to the questions. This is pretty much it for the whole lesson, actually. I'm going to go back to the questions now, so you can try to answer them. Here we are. Read the following statements, tell me if they are true or false, and answer question number 6. I think question 6 requires some calculations. On the Regents, you're only going to get questions that are broken down like this. Okay, and in class, the teacher may actually give you one single question that requires you to perform all these calculations. So it will be, for example, if given 15 grams of ice, calculate the total amount of heat, that's necessary to raise the temperature from negative 17 degrees Celsius all the way up to 137.5 degrees Celsius. So one question, that's it. And in order to answer that question, you'll have to do A, B, C, D, E. And then add your answers for all of them. Let's take a look at this, try to answer these questions. And that's pretty much it. Stay tuned for the next video, video number 5. Thank you.